Hello, my name is Patrick Altmeyer. I'm a PhD student in Trustworthy AI at Delft University of Technology, and today I'll be talking about explaining black box models through counterfactuals. I'll first introduce the problem of black boxes. I then move on to the methodology behind counterfactual explanations. What exactly are they? What are they not? And then I'll get to the core of this presentation and introduce the package that I built that implements counterfactual explanations in Julia. Start off by presenting the architecture and then providing a handful of usage examples. And finally, I'll also set out goals and ambitions for this project. So the world is moving from human to data-driven decision-making. And black boxes play a large role in this. They're being deployed in safety-critical and public domains like healthcare, autonomous driving, and also finance. And to give you an example, it is more likely than not that your loan or employment application is handled by an algorithm, at least in the first instance. And I think that this can be a recipe for disaster for two reasons. Firstly, black boxes are typically not explainable. We usually don't really know how they make their decisions or predictions. And they also learn what from a human perspective, looks like junk. So there's this classic example here from Goodfellow et al., where they show that it's relatively easy to fool a neural network by just adding structured noise. And we'll come back to this idea of neural networks learning representations or explanations for the data that don't make sense in a few different places of this presentation. Just a quick notion here. So Cathy O'Neill in her book says that you cannot appeal to algorithms. They do not listen, nor do they bend. And what she means by this is that if we deploy black boxes in the context of automated decision making, then this can create very undesirable dynamics. The operators in charge of these systems have to rely on it blindly, whereas individuals subject to the decisions generally have no way to challenge the outcome. Now, when it comes to trustworthy AI, I think about it in terms of these three pillars: ground truthing, so the data, probabilistic models, and counterfactual reasoning, counterfactual explanations. I won't cover ground truthing today. I'll very briefly speak about probabilistic models because they also play a role in counterfactual explanations. So the current standard in ML is still to rely on plug-in approximation. So we fit a neural network, for example, and we rely on the point estimate of the parameters that we get. But what we should realize is that in a setting where we're very underspecified in the data, parameters actually correspond to a diverse variety of compelling explanations and perhaps also not so compelling explanations for the data. So relating this back to the adversarial attack that we saw earlier for this panda image, there are representations in the data or patterns in the data that these deep neural networks pick up on that aren't necessarily compelling. And one way to deal with this is to just treat these models probabilistically and instead of computing plug-in predictions, compute the predictive posterior, so sample predictions from a distribution. Now, counterfactual explanations come in after the modeling stage, and we're interested in understanding how the model actually makes its decisions. And in particular, in this context, we look at how input changes lead to changes in the output to kind of emulate the behavior of the black box that we're trying to explain. And one thing that is nice about counterfactual explanations is that they're always true to the model that we're trying to explain because they work with the black box directly. And that's in contrast to some of these other popular XAI methods, such as surrogate explainers that involve approximations of the model that we're trying to explain. The framework for counterfactual explanations was first set out in Wachter et al. In 2017. The idea presented in that work is that we want to trigger a label switch in the predicted label of some classifier M here. So we want to go from, in the loan application example that I mentioned earlier, from rejection to an offer, for example, from a 0 to a 1. And we want to investigate what kind of input changes it takes to make that happen, to fool the classifier M into thinking that this factual label, now moved to a counterfactual state of the world, presents a different outcome. And typically this is done in many cases through gradient descent in the feature space or some latent representation thereof. And I've illustrated this here. This cat is moving from her factual state to a counterfactual state that will lead to a change in the predicted label from cat to dog. So some of you may have looked at this methodology and thought, well, this looks very similar to adversarial examples. So again, back to the gibbon, panda and gibbon example that we saw earlier. And that is true. There is definitely methodological parallels here. But adversarial examples are meant to go undetected. So this structured noise that we saw in this image earlier is meant to look like noise from a human perspective. Whereas in the context of counterfactual explanations, we want those to look meaningful. And the literature has come up with a number of desiderata for counterfactual explanations. For example, plausibility. The counterfactual should look realistic to a human inspector, but also more recently some work on causality. Karimi et al. In a series of papers showed that if we, and this is a big if we have causal knowledge about the inputs and outputs, then we can use that and leverage it to create counterfactuals more efficiently, and also counterfactuals that actually respect that causal structure. But of course, this is a very big if, and it may have also caused some confusion, which I'd just very quickly like to pick up on. Counterfactual explanations are not causal inference. So in causal inference, we also have the term counterfactuals. Here they are thought of as unobserved states of the world that we would like to observe in order to establish causality. And the most straightforward way to do that is still to actually interfere with the state of the world. Now, of course, there is some link to the counterfactuals that we deal with in counterfactual explanations, but it's important to realize that counterfactual explanations actually happen after the modeling stage. So we take some fitted model, we perturb the features to then investigate how the modeled outcome changes, not the true outcome. So we have not in no way magically solved causality through this literature. And if you're interested, there's a related, interesting related thread on Twitter. So when people say that they want counterfactuals to look realistic or plausible, what they really mean is that the counterfactual should be generated by the same or a similar data generating process as our actual data. And there are two approaches to this problem. One relies on the model itself. So if we work with Bayesian classifiers, they are known to have some generative properties and at least be aware about where in the feature domain uncertainty is high and where it's not. It turns out that when we work with such classifiers, then things actually get a lot easier. The other approach is to say, let's delegate this task of learning the representation, the data generating process to a separate model, to some generative model, for example, a VAE. And then instead of traversing the feature space, we traverse this ideally lower dimensional latent space, which has the data generating process encoded, embedded in itself. So we will end up with counterfactuals that look more realistic. And I'll have a few examples for this later. Finally, moving to the core of this presentation, counterfactual explanations in Julia. So up until recently, the work in this field was scattered across different GitHub repositories. Then last year, this Python library was released, Scala, which is quite comprehensive. It has a lot of different approaches included, but it is not language agnostic, and more importantly, it's also not composable. So each different approach is treated as its own entity. And we also, up until recently, have been lacking any support for this kind of work in Julia and in R. And with this work, we try to change that. We provide a unifying framework for generating counterfactual explanations in Julia, but also for models trained in other languages. So leveraging Julia's support for interoperability, we've also recently added support for torch neural networks trained in R and Python. The package is designed to be very easily extensible through this patch, and it's also designed to be composable in the sense that users and developers will hopefully find it very easy to combine ideas, different ideas and approaches that have been put forward in the literature to generate counterfactuals. And we'll see in a moment what exactly I mean by that. So the package is built up of a number of submodules. Some of them deal with data and data preprocessing, and related to this also generative models. There's a simple variational autoencoder architecture that can be used to learn this data generating process. And then there are these two core modules here that deal with declaring model types and the different counterfactual generators. And all of these different submodules produce ingredients that are fed into the main API call, generate counterfactual, that then generates counterfactuals. And just zooming in on these two important submodules here. So generators, the way it's built up is that we start from a base abstract type that is subtyped. Right now, I focused on gradient-based counterfactual generators, and then various subtypes that implement specific approaches that are gradient-based. But you can see that there's scope to extend this in the future to also include generators that are not gradient-based. And similarly for models, I've started focusing on differentiable models, but all of it starts from this base class abstract fitted model. So in theory, we can also extend this tree here and add support for other types of models and classifiers. Moving on, the basic usage. So we'll see a handful of examples now where I, using some toy data that is available as an artifact from the package, first create the data, then select a random sample in one of the two classes, and then generate counterfactuals, essentially sending this randomly selected sample from one class to the other using different approaches. And we'll start off with a generic generator. So we always begin by instantiating an abstract fitted model. In this case, we're using this logistic model, which is really just for illustrative purposes. So a linear classifier and its coefficients. Then we define our target, as in the opposite of the predicted label. And here we have our standard API call. So we define our generator, and then we generate counterfactuals by feeding these different ingredients to the main API call. Et voila, here we go. This is the output of the generic generator. So again, we're doing gradient descent in the feature space, sending the sample across the decision boundary to then be classified with a certain desired probability as class 1. Now moving on to another generator. So this one relies on a Bayesian classifier. So here for illustrative purposes, I have a Bayesian logistic model. Again, I define my target, and I then perform a greedy search as proposed in Schut et al., the paper that I mentioned, that I pointed to earlier, that works in this setting with Bayesian classifiers. The API call is the same, and the output looks like this. So now we have this Bayesian classifier that once again is aware of predictive uncertainty. But in this case, we actually end up with a counterfactual that looks quite similar. Now moving on to the different approach to probabilistic modeling, the revise generator, which relies on search in the latent space. So I have a specific composite type for this generator, so users can use that. But here I'm trying to show that you can also compose this yourself by just using the main API call and specifying latent space search to be true. This will then trigger a generative model to be learned. And these two code chunks actually yield the same result. And I think this illustrates that really what this revise generator does is the same as a generic generator, but searching in a latent space instead of the feature space. And I've also combined this here with the Bayesian classifier, in fact. So again, these ideas can be combined. And here we see the outcome. We can see that it takes fewer steps here, which is probably due to the fact that we're moving in this latent space. In general, the latent space, since it is typically lower dimensional, will accelerate the actual counterfactual search. Of course, you have the engineering overhead of actually training the generative model. And things actually can go wrong if we rely on latent space search. And I'm going to illustrate this here very briefly. So taking these ideas now to MNIST data, this is all just loading the data from artifacts, loading a pre-trained VAE, in this case, a very expressive VAE, and the output is quite staggering. So we're trying to turn a 9 from the factual value to a counterfactual state where the model would think it's a 4. And this is clearly from a human perspective, looks like a 4. But things can go really wrong. If the VAE, and here I'm using a less expressive one, if it's poorly specified, then it can be the case that, as we can see here, even though this image on the right does look like a 9 from a human perspective, or at least more like a 9 than a 7, the MLP that we have running in the background that is classifying these images does not think that this is a 9. It's still convinced that this is a 7. Actually, it's pointing out that it looks like a 4, which is plausible. But the same MLP can also be fooled by something which very much looks like an adversarial attack. So here I just use generic search, and you can barely make this out here, but there are some tiny changes to some of the pixels in regions far away from where the digits are typically drawn. And our model does think that this 7 has now been turned into a 9. And again, I think this illustrates this idea that I mentioned earlier, that in the deep learning setting or the black box setting in general, the models might be learning patterns in the data that aren't really plausible from a human perspective. My view on this is that this should come through in our counterfactual explanations. So I would always start off with just generic search to see results like this, to then understand, okay, the model is perhaps just not very, very robust. But this is a topic for debate. So moving on to some of the interesting features of our package. Customization. It is very easy to extend this package. And here I'm giving the example, again, in the MNIST setting, using this time a deep ensemble instead of an MLP. Again, this is pre-trained. All we need to do to make this flux model compatible with our package is to declare a subtype of the abstract fitted model, feed it the actual model object, and then implement these two method extensions for the logits and the predicted probabilities of our model. And here we can see the results again on just focusing on the two charts on the right. So this is using the generic and the greedy approach for the deep ensemble, trying to turn a 9 into a 4. We're not using any separate generative model to learn any latent representations. We're just relying on the properties of deep ensembles to learn predictive uncertainty. And we can see that the resulting counterfactuals are more plausible than perhaps these other two panels on the left that again look like adversarial attacks. Custom models, that's also an interesting story. Well, it's still the same story, but now looking at interoperability with other languages. So I'll skip the details here, but if you want, you can take this offline and look at the very few code changes that were really necessary to add support for torch models trained in R. The API call ends up being the same as we would want it to be. And here's just an example of explaining or generating counterfactual for a neural network that was trained in R, so completely outside of Julia. Custom generators, I'll breeze through this one. Adding additional generators is similarly also quite easy. So here I added this generator that uses dropout on the features in the counterfactual search, and really the only lines of codes that were necessary to get from this to the same API call are those code chunks on the left. Finally, moving on to goals and ambitions for this package. So we're at JuliaCon, so all of these steps here are done. But there is lots of stuff to do. I would like to add support for more generators, such as the ones listed here. I would also like to add support for other models, MLJ, GLM, but also non-differentiable models. Enhance the pre-processing functionality for the data, and also extend perhaps the functionality to regression problems. That would be interesting. And I'd also like to use flux optimizers instead of, at this point, the gradient search is implemented from scratch. It would be nice to rely on flux here. And finally, to wrap this up, just leaving you with a handful of resources. So there are two separate blog posts that I wrote, one introducing the idea behind counterfactual explanations, and one introducing the package. It's already a little bit out of date at this point, but still perhaps interesting for some color. Then there are, of course, the package docs, and there's a small contributors guide as well for anyone who would like to get involved in this work in the future. And that's actually one of the things that I hope to achieve with this presentation. It would be really nice to get some people who are similarly excited about the topic of counterfactual explanations involved in this work to reach all those goals that I set out on the previous page. So with all of that, thank you very much. I hope you found it interesting, and hope to hear from some of you moving